The foundation for what we use for a lot of the material in the following weeks is a bell-shaped curve. So this is a form of data that we see often when we collect information, collecting numerical variables. The idea of, in terms of what's expected, the mean usually has a high probability, so we get a lot of data in the middle, and then as we get further away from what's expected, either larger or smaller, it becomes less and less likely. So that wording kind of describes this bell-shaped curve where it's symmetric, it's focused around what we expect to happen, but then there's some variability to the data where the frequencies decrease as we get away from what's expected. So the symmetric model is built around two things, mean and standard deviation. So when we get these curves, we'll have to describe the mean that we're looking at and the standard deviation. Now, with the models that we look at in this section, it's going to be built around population data. So the means will be using our symbol mu, and standard deviation will be using our symbol sigma. Another thing that we want to notice is our number line that we'll have underneath the bell-shaped curve is a continuous number line. So we can land absolutely anywhere on this number line. But what we can do is get an idea of the scale that's used based on the mean and standard deviation. So what we're going to do here is look at this annual rainfall in Portland, Oregon. It's unimodal, so we have our single peak, and it's approximately symmetric. So that's going to describe our bell-shaped curve. Then they go on and tell us about the mean of 40 inches and standard deviation of 8 inches. And we're rounding to the nearest inch there. So with those two pieces of information, we can get an idea of center and spread. That's what we're getting from mean and standard deviation. So with these bell-shaped curves, when they tell us the mean, that's always going to go right in the middle. So that'll be the middle of our bell-shaped curve, is in this case 40. Then what I want you to see is this notation to the left-hand side here. It matches up with notation that we saw with binomial distribution, and we use this random variable x to represent what we're looking at. In this case, it's this idea of annual rainfall in Portland. So we have this variable, and how it's measured is that letter n is telling us that the shape of the distribution is normal. So when we see that capital N, we can immediately imagine a little bell-shaped curve. And then the order of the values inside of those parentheses will always go mean, standard deviation. So in this section, if they describe a bell-shaped curve, what we can always do is use this shorthand notation of saying our variable x is defined by a normal curve based on some mean and some standard deviation. So in this case, with the rainfall in Portland, we see it's normal with a mean of 40 and standard deviation of 8. Now, standard deviation, what that tells us is the scale for the jumps in the number line. So we move number to number, we want to use a scale of 8. So if we're moving above our mean of 40, our next value would be 48, and then add 8 to get the next number, and add 8 to get the next number. So we get this number line going. And then the same in the opposite direction, so 40 minus 8, 32 minus 8, and 24 minus 8. So we can get this whole number line based on mean and standard deviation. And with that, we can start seeing what numbers we expect and what numbers we don't expect to happen. Like if rainfall in Portland is 24 inches up to 56 inches, that's pretty expected. But say one year they said they had rainfall of 70 inches, which we can now tell from our number line is way out there. That is very unexpected, and we want to check that data out. So mean standard deviation gives us a scale going there. Now, once we have the scale going, we can start thinking about probability. Even with the wording I just used in terms of what's likely and what's unlikely, we can get more exact values for probability. And probability in this section is based on area under the curve. Now, if we have our whole bell-shaped curve, the total area under the curve is 100%. And just like with other sections, in terms of calculations, we'll be working in decimal form. So really everything adds up to 1 under the curve, but that translates to 100%. So then what we want to do is look at portions of those areas. Like, what if we want to look for the probability being less than some number, or more than, or between? So that's where we can start looking at area under the curve as probability. Probability is an area. So if we want to look at x being less than or equal to some number, if we have our bell-shaped curve, what we want to find is wherever that number is landing, we'd want to find the area under the curve that's less than or equal to that number, and that area would be our probability. Same thing for if we're looking for more than or equal to some number, we'll find this area going above. And then we could also look between two values. So x could be bounded by some lower value and some upper bound value. And with that, if we find the area between those two values, that would be our probability. So we're going to have this mixture of kind of cutoff scores, like wherever the area is ending is some x value that we're looking at. And it's just with 2, we'll have 2 different x values. So we'll have these cutoff scores, and then we'll also have area, and the area is going to relate to probability. Now, a case we want to be careful of here that we can't do is the probability of an exact value, looking for probability that x is some number. So what that would look like in terms of our curve is we'd have our curve, and then wherever that value for x is landing, so that's our cutoff value, and trying to find the area of just that one instance, we can't do that in this section. If you try to do that, your probability is going to come out to 0. And it's because, in this case, probability is area, and a line itself doesn't have any area to it. So we can't find probability for exact values. We need to use other methods for that. What's kind of nice about that, though, is when we get to word problems and they say they have wording like versus if we're looking at this less than or equal to case, if we said at most 2, so saying we want to look at the probability of at most 2, that would be looking at x less than or equal to 2. Now, if the wording of the question said less than 2, that would technically translate to not having equality. However, in this section, because there isn't a significant difference from being at 1.9999999 and being at exactly 2, due to this restriction of not being able to find probabilities of an exact value, what we get to do here is just use less than or equal to 2. So in these sections, using probabilities with normal model, you don't have to worry about if it has equality or not. We can assume we have equality based on the fact that a line doesn't have any area to it. That was something we had to be careful of with binomial and discrete random variables, but now there's a little more flexibility just because we're looking at area. All right, so while we'll get to calculating exact areas, what we can do is use this rule. It's a 68, 95, 99.7 rule, or more commonly called the empirical rule. And it's just a way to get kind of quick estimations without a calculator for how these probabilities distribute. So say we have this curve here, and let's even use just its normal curve with some mean and some standard deviation. So if I set up my line, mean's right in the middle. If I go 1 to the right, that's taking my mean and adding 1 standard deviation. If I move to the left, it's bumping down 1 standard deviation. What the rule says is that if we're looking at this area between 2 values and it's within 1 standard deviation of the mean, if I'm trying to find this area, it should be about 68%, roughly. And these are estimates. We're going to improve on these once we get using our z-table and making calculations. But for now, without those resources, if we're looking between those 2 values, 68% between those. If we look between 2 standard deviations, so we take our mean plus 2 of those standard deviations, that mean minus 2 of those standard deviations. If we look for the probability of being between those 2 values, That is about 95% of the data. And then if we go and stretch out to 3 standard deviations, which is way out there, which you can see in terms of area under the curve, we're getting very close to the whole area, which would be close to 1. And if we found the area between those two values, that's going to be about 99.7%. So pretty much 100% if we round into a whole number there. So with this, we can get a little rule too of kind of what's expected and what's unexpected. If you're landing outside of 2 standard deviations, we consider those values unusual. Basically because there's a 95% chance, or rather roughly 95% chance of landing between those. So there's only a 5% chance of being outside. That's where we consider those values unusual. And then if we even stretch beyond 3 standard deviations, that's extremely rare. So we get an idea of what's expected and what's not expected. All right, let's try out using this empirical rule, and then we'll get to finding exact calculations. So we're going to use that same example with the Portland rain, where we're centered at 40 and have a standard deviation of 8. So with that, we can get our number line going. So 40 in the middle, and just mimic what we did up there before. And then we can start asking questions about percentages and probabilities. So with this first question, what percentage of the time is the annual rainfall between 32 and 48 inches? So what we're looking at this one is starting at 32 and then going up to 48. So this is a question of looking within 1 standard deviation, which according to our empirical rule, that should be about 68%. So with that, there's about 68% chance of getting between 32 and 48 inches of rain. The next one said, what's the probability of getting more than 48 inches of rain? Now with this one, we're starting at 48, and then we want to find the area above. And this one we need to think a little bit more about. So with the empirical rule, it's always giving us this probability between 2 values. So what we can see is if we're within 1 standard deviation, that takes up about 0.68 of our area under the curve. Now remember, that all has to add up to 1. So between knowing that everything should add up to 1 and having symmetry, so we have these 2 unknown sides. We don't know what's over there, we don't know what's over here, but those 2 values should be the same. So what we can do is figure out what area is left over. So if we take our 1 and then take out that 68%, we have this 32% left over. But we need to divide that up evenly between the 2 sides, so we want to cut that in half. So what you'd find is that on the right-hand side we have 0.16, and on the left-hand side we have 0.16. So with this empirical rule and using symmetry, we can take out what's in the middle out of 1, and then cut it in half to see what's happening in each of the tails. So for this case of looking at 48 and larger, we can see that area is about 0.16. Again, all of these are estimates. So we could say about 16% for that area. What percentage of the time is the annual rainfall 24 inches or less? So with this one, we're heading out to the 2 standard deviation spot, and we're going to look at the tail. So again, we need to do a little math to figure out what's happening in the tails. But with that 2 standard deviation rule, we know that in between is going to be 0.95. So what we could think about is, okay, everything has to add up to 1, take out that 95%. So we have this 5% left over, and then cut in half to divide it up between the 2 tails. So on the right-hand side, we'll have a 0.025, left-hand side, 0.025. So with that one, if we're looking for this area on that left-hand side, that would be about 2.5%. Then 56 inches or less. With this one, we're starting at 56, and then we want everything less than. So when you see these, I always like to draw a picture when I'm doing these calculations, because what I can tell right now is this is going to be a big probability. If you shade large area, it's going to be large probability. And like C, it was a tiny area, so it linked to a tiny probability. So you can get an idea of the scale and kind of intuition about what's going to happen by drawing a picture. So with this one, we're out at the 2 standard deviations away spot. So we know in the middle we have a 0.95. And from before we found out our 0.025 in each of the tails. And what we want to grab is the 0.95 and the 0.025. So what we want to do is combine those two values, which we would just add them up. So add those two areas for a 0.975. So about 97.5%. With the next one, we say, what's the probability that the annual rainfall is 54 inches or less? Well, with this one, when we go to our picture, we don't see 54. We can have an idea of where it's landing. It might be about there-ish. And we can get an idea, okay, it's going to be less than 97.5%. We could probably get a lower bound for it. But through the empirical rule, we can't do it. And what's key is that this value that's coming through isn't exactly a certain number of standard deviations away, or at least not a whole number. It isn't exactly 1, 2, or 3 standard deviations away. And with that, we can't use the empirical rule. And really, this is the case that happens most often for the problems we're going to look at in this section. Empirical rule is great for when you land on those exact values, and then you can get an idea. Again, all of those are estimations. We would have to go to the z-table to get the exact answers. So when we get to these problems, what we're going to have to use is something called the z-tables. And before we even do that, we need to figure out how to calculate z-scores. So that's going to be in the next videos, is looking at these cases where, what if we aren't landing exactly 1, 2, or 3 standard deviations away? What if we want exact probabilities? But this was to get us familiar with the bell-shaped curve and how these probabilities distribute, but most often we won't use the empirical rule, but it's a helpful tool.